All right, so in the interest of time, we are going to move on. So looking at discontinuity and continuity, whether a function is continuous or discontinuous, or when is it discontinuous, and we were actively taking information based on whether the what is meant by a continuous function, the types of continuity. We also look at the types of discontinuity and how to prove that a function is continuous. All right. So what we're going to be doing is to be going through some questions on this so as to ensure that we can familiarize ourselves with how to work out these questions. Oh, let me just save this for you guys. So we're looking at continuity and discontinuity. So we learned that if a function is continuous, right? So if f of x is continuous, at x equal to some number, let's say x equal to a, right? Then we know that the following conditions must be met. F of a must exist. All right, 2. The limit as x tends to a of f of x must exist. And 3, the limit as x tends to a of f of x must be equal to f of a. So once these conditions are satisfied, then this means that the function is continuous at a point. All right. Let's see if we can, put this into practice. Let's see what this looks like in an example. So we're going to be testing to see if this function is continuous at x is equal to 1. All right. So let us see what this looks like. Let me use a different color for the solution. Now you would bear in mind that the function must exist. So when x equal to 1, right? So that means f of 1 must be equal to 3 times 1 plus 2. So this is going to be 3 plus 2, which is going to be equal to 5. All right. So definitely we know that the function exists. Hold a second, please. Right. So here it is. We know that the function exists. Part 2, the limit of the function must exist. All right. So we're going to look at it two ways. When the when it is approaching from the left hand side and when it is approaching from the right hand side. What do we mean? Left hand side and right hand side. Say for instance, this is our x and y axis. Just for argument's sake. This is 0, this is 1, 2, 3. Then you have 0, -1, -2. And we can just put a few numbers here. Not necessary, but now if you think about the number 1 that x is equal to, which is this number right here, there's two ways you can approach this number. You can approach this number coming from the right hand side, and you can approach this number coming in from the left hand side. All right. So we can approach the number going to the right. Yeah. We can approach the number going from the left hand side, and we can approach the number coming in from the right hand side. Right. So there are two ways to approach the number. All right. So we can check it from both. So the left hand limit, thank you. So the left hand limit must equal to the right hand limit, right? So that's one of the things that we check for. As well. Once we have proven that to be so, then we know that the function so from the left hand side and from the right hand side. So it is the limit as x approaches 1, and we put a minus at the top. The minus is telling us that we're coming in from the left hand side, right? So that's what it is telling us, that we're coming in from the left hand side. So it is going to be as it comes in from the left hand side of f of x. So that's going to be equal to, all right, I have to write it down below because I don't want it to come too much on this side. So it's going to be equal to the limit as x approaches 1 from the left hand side of 3 times 1 plus 2. So that's still going to be equal to 5. And the limit as x approaches 1 from the right hand side of f of x, that's still going to be equal to the limit as x approaches 1 from the right hand side. So we're going to have 3 times 1 plus 2. So that's still going to be equal to 5. And you remember we do limits. You have the direct substitution. So direct substitution is when you take the value of x to be equal to the number that it is approaching. So we say the limit as x approaches 1. So it's when x is equal to 1, right? And then the last part we have to do is to show that the limit as x approaches a of f of x is equal to f of a. We clearly see, and we can make a little note of it. We should put f of x right here. So we specify that it is as it approaches the particular function. So what is it that we just prove? We just prove that the limit as x tends to 1 of f of x is equal to f of 1. Because notice when we did f of 1 was equal to 5. And then when we did the limit as x approaches 1 from the left hand side and the right hand side, that's also equal to 5, right? So f of 1 is equal to 5, and the limit as x approaches 1 from both the left hand side and the right hand side is also equal to 5. So we prove this to be true, that to be true, and we also prove that the limit as x approaches 1 of f of x is equal to f of 1. So that means we also prove that to be true. That means that this function is continuous. So we prove that the function is continuous as x equal to 1. Let me give you a little bit of time to write, and then we look at a case where the function is not continuous, so you can see the difference. All right, so one of the types of functions you're going to learn about in terms of checking for whether a function is continuous or not is what we call a piecewise function. All right, so sounds strange, sound unfamiliar because we're not used to it. So we're going to be looking at piecewise function and check to see if the functions that we get, whether they are continuous or not. All right, everybody should be finished writing now. Anybody still writing?
No, sir,
Alright,
finish.
All
so
right,
about
Sc-
that.
scroll up a bit.
Yes, sir. Just don't want to see if you miss something.
All right, this is where we started.
Oh, this very good.
Okay.
Like, my reference, sir.
You have it now?
Yes, sir.
Okay. All right, so we want to prove if this function is continuous x is equal to at x is equal to 3. All right, so we're going to check it for both cases and see what is it that we end up with for our answer. So when x is equal to 3, f of x is equal to, for both functions, negative 2 times 3, we get negative 6. And then f of 3, well, we could have put f of 3. That's going to be equal to negative, oh, well, it says when x is equal to, when x is equal, when x is equal to 3. So, and we should have pointed out this to you earlier. All right, so when we talk about how it's going to approach, 3. All right, let me do it over this side. 1, 2, 3, 4. So this is 3, 4, 2, 1, 0. So if we're approaching 3, we're going to approach 3 from both sides, from the left and from the right. So when it says that you are less than 3, it means that you are not exactly 3, but you are close to 3. And then when it says you are equal to 3 or greater than 3, that means it's everything that is on the right hand side. Once you're less than 3, that means you are on the left hand side. So notice it says that we are to prove if this function is continuous at when x is equal to 3. All right. So we want to prove that when it is equal to 3. So over here, this would be when it is approaching 3 from the left-hand side. All right. So let's look at what we get. Let's continue working this. So it's going to go into that writing. So f of 3 is equal to negative 3 squared plus a times 3 minus 16. Negative 9, 24 minus 16, negative 25 plus 24 equals to negative 1. So because right away we realize that the, the answers are different. So because they're different, this is going to tell us that this function is not continuous. All right. So let's continue. So this is when it is approaching from the left-hand side or the left-hand limits. So notice this is step 1. When it says f of a must exist, right? So when x is equal to 3, well, let's use this part alone because ideally it is just this part alone when x is equal to 3, because this is the part where x is equal to 3 right here. So we have to use this function for when x is equal to 3 or greater than 3. Now, the limit as x approaches 3 from the left-hand side of f of x, from the left-hand side, we have to use this function because left means that anything that is less than 3. So that means that you're coming in from the left-hand side. So you'd have to use this function because this is where x is less than 3. So this is going to be equal to the limit as x approaches 3 from the left-hand side of negative 2 times 3. So this is going to give us negative 6. And then the limit as x approaches 3 from the right-hand side, which is this up here. So we already did work it out. If you want to work it out again, of f of x is going to be equal to the limit as x approaches 3 from the positive side, negative 3 squared plus 3 times 8 times 3 minus 16, which is going to give us negative 1. So since the limit as x approaches 3 from the left-hand side of f of x is not equal to the limit as x approaches 3 from the right-hand side of f of x, so they are not equal, the function is not continuous. Not continuous at x is equal to 3. All right, because it's not equal for both of them. One of them it's equal to negative 6, the next one is equal to negative 1. So in order for it to be true, you must get the same answer. All right. So notice what it says up here. So f of a must exist, the limit of it must exist, and the limit of it must be equal to, well, so basically put it this way. Number 1 and number 2 must be equal to each other. All right, so that's the third condition. The answer that you get for number 1 and the answer that you get for number 2 must be equal to each other. If they are not the same, then that tells you that the function is not continuous.
Sir?
Go ahead.
I'm kind of lost in sir. I don't understand this, sir.
All right, not a problem. Let us work through a few more questions because the idea is you're learning it for the first time. So this is understandable. One of the things that I'm going to ask you to pay attention to when we're working out the question is this. If it is continuous or discontinuous, what are we looking for? All right. So I'm going to look at another question where it is continuous, and then we're going to look at another question where it's discontinuous, and then see if that can further help you to get an appreciation of, you know, what is happening with the different functions. All right. All right, so just bear in mind when it says a function is continuous, it simply means that if you were to put your pen on the paper to draw this function, you can draw it without removing your pen from the paper. So take for instance, if I have a function like I'm going to draw a curve and I can just do that, that means I have a continuous function. But there are some functions that are discontinuous, and then I'm going to show you how to draw those functions that are discontinuous. They have a jump. So we're going to look at what is a jump discontinuity. We're going to look to see how that looks on the graph. So like for this function now, because you get two separate values for x, this would be a jump discontinuity. All right. So you get a jump discontinuity for this function. All right, take this off and then we look at a few more where we can just, try and break it down as simple as we possibly can. All right, let us look at another question.
Yeah, well, 1 second, James. Oh,
Okay,
it's all right out this.
all right. You need more than what you're seeing on the screen now?
So just the part was a since.
Right here, so? Or,
Yes, sir, that part.
oh,
So how much more lesson we have left back?
well, you have quite a few because after this class, we're going to start looking on integration. And we have about 3 classes of integration because remember, we have next week and we have 2 weeks in April.
And then examine in April.
And then exam, right?
Alright, so
All right, let's look at this function and see if it is continuous at x is equal to 2. All right. Now, for the function to, first and foremost, we're going to check to see if the function exists when x is equal to 2. All right. So at x is equal to 2, then f of 2 is going to be equal to, we're going to use this function, because for this function, notice the piecewise function is telling us that this function is relating to two other functions. This part is quadratic, this part is a linear. So we're going to look at it and see if we can even put it on the graph to show you what it looks like. Now, when for this function, which is a quadratic, how do we know that it's a quadratic? Because the highest power of the variable is 2. We are using values for x that are less than 2. And for this part that is the linear, because it's linear, because the highest power of x is 1, we're using values for x that are equal to 2 and greater than 2. So when it says at x equal to 2, we're going to use this function right here. So we're going to have 2 times 2 minus 3. So that's 4 minus 3. So that's equal to 1. So f of 2 exists. So that's the first thing. Let us look at it. We know that f of 2, it must exist. We find that f of 2, we get 1. 1 is the value that you're going to get when you substitute x equal to 2. So right then and there, we know that it exists. It's not infinity. So we know that it exists. Now, let's think about it. 0, 1, 2, 3, 4. So 1, 2, 3, 4. I can approach 1 from the left hand side as I can approach 1 from the right hand side. So going in from the left hand side, going in from the right hand side. That's how you can approach. Notice the language I'm using, how we can approach. So that's why it says when we're using the approach, we have to look at the limit, because this is as x approaches a, right? We look at that language when we looked at limits. The limit as x approaches a, right? So one of the rules of limits that we learned is direct substitution, right? So this is part 1 then, so to speak. Then part 2 is to find the limit as x approaches 1. Let me tell 2. 2 we using, I'm the right one, sorry. 2. So this is the number 2 we're using. So as x approaches 2 from the left hand side. So if x is approaching 2 from the left hand side, that means I have to use this function. Why am I going to use this function? Because all values that are less than 2 are on the left hand side. So that's why I'm using this function. So it's going to be f
Say
of
that again.
x. All values that are less than 2. See the numbers them over here. So 1, -1, and -2. These are numbers that are less than 2. 0 is less than 2. It's on the left hand side of the number. See the number here, so in the middle, I have a left hand side of the number, you have the right hand side of the number. So the numbers that are less than 2 are on the left hand side. So if I am approaching 2 from the left hand side, it means those numbers are less than 2. Which function have values that are less than 2? See it here, where x is less than 2, you're using this function. Less than 2. See it here, that's why I say every time I'm doing the question, I use this information right here. So you can see what we're saying if we're approaching from the left hand side or on the right hand side. So it's going to be the limit as x approaches 2 from the left hand side is going to be 2 cubed, let me enter 2 squared minus 3, which is going to be 4 minus 3, which is equal to 1. And then you look at the limit as x approaches 2 from the right hand side of f of x. From the right hand side is numbers that are greater than 2. Yes, you can approach 2 by coming in from the right hand side. So those numbers are greater than 2. If the numbers are greater than 2, that means I have to use this function. So it's going to be the limit as x approaches 2 from the right hand side. It's going to be 2 times 2 minus 3. So that's 4 minus 3. So that's 1. So notice here now, right? So we know that since the limit as x approaches 2 from the left hand side of f of x is equal to the limit as x approaches 2 from the right hand side of f of x, right? So we know that it exists. We see that it exists, right? So the function is continuous as x equal to 2, right? So this is how we can check if a function is continuous or not continuous. So we just check it in. We're going to represent this on the graph to see what it looks like. We're going to represent this on the graph and see what it looks like. So you can see how such a function would look on your graph paper. And then when we get one that is discontinuous, we're going to show it on the graph as well to see how that would look on the graph paper. Anybody still writing? All right, I take that as a no. So let's look at one. Let's look at the graph real quick and then we'll look at another one that So what we can do is choose some values for x for this function. Yeah, just a few. So x, and what we will get over here is our f of x value. So we're gonna start with x is equal to 2 and values that are less than 2. All right, so when x is 2, 2 squared is 4 minus 3. That's going to give us 1. When x is 1, 1 squared is 1 minus -2. When x is 0, 0 squared is 0 minus 3, -3. When x is -1, -1 squared minus 1, -2. When x is -2, -2 squared is 4 minus 3, 1. When x is -3, -3 squared is 9 minus 3, 6. So these are our coordinates that we're going to use. 2, 1, 1, -2, 0, -3, -1, -2, -2, 1, and -3, 6. So we're going to use these coordinates to plot this graph. We're going to use the same. So f of x is equal to 2x minus 3. Well, this one is a straight line, so we don't need a lot of points to draw this straight line. To draw any straight line, you just need 2 points. But we're going to use 2, 3, and 4. So 2 times 2 is 4 minus 3. That's going to give us 1. 2 threes is 6 minus 3, 3. 2 fours is 8 minus 3, 5. So we're going to plot 2, 1, 3, 3, and 4, 5. So those are the points that we're going to plot to get that line. So we have the x-axis and we have the y-axis. 1, 2. All right. So to draw this graph, remember this is when x is less than 2, and this is when x is greater than or equal to 2. Now, because it says x is less than 2, so x cannot be 2. So where you have this point, you're going to use an open bubble. All right. So when x cannot be 2, so for this point, yeah, you're going to use an open bubble for this point. Let's go again. X cannot be 2. If you're less than 2, you cannot be less than 2 and be 2 at the same time. So if I say you have less than $1,000 in your pocket, right? Then I cannot then go and say you have $1,000, because less than the amount and the same amount is two different things. Yes. So you have to use a open bubble to represent this point, because x cannot be 2. So the first point is going to be 2, 1. So 2, 1, open bubble. 1, -2. So 1, -2, that's a point. 0, -3, that's a point. -1, -2, that's a point. -2, 1, that's a point. And -3, 6, that's another point. So we're going to have our curve. Let me use a different color. You're going to have your curve coming down and then going up right to this point. So it's an open bubble. So it would be a bubble. But here now is where the continuity comes in. Notice this is an open bubble, which means that this point is not part of the solution. But where this function left off, this one picks it up, because now in this one, x is 2. But here, so x cannot be 2. But here, x is 2 because it says it's greater than or equal to 2. So we use a solid bubble. So your first point is going to be a solid bubble. Notice 2, 1, open bubble, but 2, 1, you have to use a solid bubble. So where this one left off, this one picks right up at that point. So you can't use this point because it's an open bubble, but then you have to use the point because where this function left off, this one picks up right there. All right. So we're now going to have, for the point 2, 1, you're going to have a solid point, and then 3, 3, another solid point, and then 4, 5, and then you're going to have a straight line continuing. So this is the reason why this is a continuous function, where one function stop, the next one picks up. All right, so it continues. So it's almost like you're running a relay, right? So the relay is such that the button must leave from one hand and into the next person's hand. So where one person have to stop, the next one gets the button and continue. There is no case where you running with the button, drop the button, and then the next person who should be the one receiving without getting the button just run or just continue the race, right? So there's not a case like that. In that case, we know so them drop the button, so now it becomes discontinuous. You will have in some races, persons will drop the button, try to pick it up, and then continue with the race. But then we know what happened in cases like those. Those persons would, normally finish last and whatever. So the idea is, in order for it to be a continuous race without any interference, any interruption, the baton must go from one person into the next and then on to the next. And by so doing, you get a fluent race. And if you have fast members, you may win. But that is how it is continuous. Anything outside of that, discontinuous. All right. So that's one case of continuous. We're going to look at another case of discontinuous and see if we can see what's the difference between the two. Anybody still writing from here? Anybody still writing? All right, take that as a no. I'm going to continue. So if, for instance, we have f of x is equal to negative 9x when x is less than or equal to 2, and x squared minus 2x plus 3 when x is greater than 2. So we want it at x is equal to 2. We're checking to see if it is continuous or discontinuous at x is equal to 2. So we're going to see what happens if it is continuous or not. When x is equal to 2, we have to use this function because this is where x is less than or equal to 2. So f of 2 is going to be equal to negative 9 times 2, which is going to give us negative 18. All right. So remember, 1, 2, 3, 4. We can approach 2 from the left side or the right side. So if we're approaching 2, the limit as x approaches 2 from the left-hand side of f of x is going to be the limit as x approaches 2 from the left-hand side. From the left-hand side, it's going to be numbers that are less than 2. So we're going to use negative 9 times 2, negative 9 times 2 is equal to negative 18. And then the limit as x approaches 2 from the right-hand side of f of x is going to be this function because this is where the numbers are greater than 2. So it's going to be 2 squared minus 2 times 2 plus 3. So this is going to be 4 minus 4 plus 3. So that's going to be equal to 3. So notice when it approaches from the left-hand side and when it approaches from the right-hand side, you get two different answers. So we can say since the limit as x approaches 2 from the left-hand side of f of x is not equal to the limit as x approaches 2 from the right-hand side of f of x, the function is not continuous. Is it any clearer? So Griffiths, is it any clearer to you?
Somewhat, sir. May I pick up now, sir, how it a go?
Okay.
I pick up a little bit.
Anybody else? Anybody else have any questions? Go ahead. Anybody else have any question?
Yes, sir.
Mm-hmm.
How this work is that you have to follow the step them when you give earlier, right?
Right.
So when I get the function, the top one, like now we are the top one say less than or equal to 2,
Yes.
and then when you do the limit is the negative and positive. I use the number way less than or greater than.
Because remember, once you say the negative, it's telling us that it is approaching 2 from the left-hand side. And when you say positive, it's telling you that you're approaching 2 from the right-hand side. And remember, one of the first rule that we look at when we were simplifying limits was using direct substitution. So even though we're saying that we're approaching 2 from the left-hand side or the right-hand side, that doesn't mean we're using a number that is less than 2 or greater than 2. We're using 2,
So can you hear me?
but yes, I come into you, but it's based on which function will you use when it is less than 2, or when you're approaching 2 from the left hand side? Which function will you use when you're approaching 2 from the right hand side? That is the difference. Yeah, go ahead now with your question. Go ahead. I'm hearing you loud and clear now. Hearing you. You can go ahead and speak now. Is the person still there?
Can you hear me, sir?
Yeah, man, go ahead.
Hello?
Yes, go ahead. Is anybody else hearing me? Are you guys hearing me? Hello? Anybody else hearing me? Anybody else in the class hearing me? Sir Griffiths, are you hearing me?
Yes, sir. Loud and clear.
Okay. All right. Still writing? Anybody still writing?
Sir, I finished, sir.
Okay.
Mhm.
All right, let's see what this looks like on the graph. But this is when the values of, wow, greater than 2. This is going to be huge. Less than 2. Yeah, this is going to be huge. All right. Not going to represent this because this is going to be huge on the graph. Because notice this goes all the way down to negative 18. So that's going to be huge. Yes, yes. All right, so for this one, we got two values of x, so we're gonna check this one as well. Check and see what is happening. All right, so let's look at what we would get for the solution. So f of -3 is going to be equal to -3 plus 1, -3 squared, 2 times -3 plus 2. So this is going to give us -2 over, this is going to be 9 minus 6 plus 2. So -2 all divided by 5. So f of -3 is equal to, this is equal to -2/5. So this is continuous at x equal to -3. Why can we say it's continuous? Because when x is equal to -3, we get a value for x, right? Which would be, in our case, the y value, because that's the value that we're going to use to represent the coordinate. Or in other words, you get a definite value. All right. So it doesn't go off to infinity. So you get a specific value, you get a definite value when x is equal to -3. So that tells us that the function is continuous at that point.
Sure.
Good.
You can just scroll up, look at just a screenshot here and write down
Which part?
the instruction part.
We can zoom out a little.
All right, sure, thanks.
Yeah, man.
Yeah, that's all. What that x minus values? Find x.
Oh, no, slash x values. Slash x dash values. So x values. Right?
As
So, yeah, man. All right. So one of the things we're going to look at is what is happening here with number 2. Because if we say, let's say when x is equal to 2, then f of 2 is going to be equal to 2 plus 2 all divided by 2 squared minus 4. So this is going to be 4 all divided by 4 minus 4. So we're going to get 4 over 0. Can't divide by 0. So we know that this is undefined. And then when x is equal to negative 2, we're going to get f of negative 2 is equal to negative 2 plus 2 all divided by negative 2 squared minus 4, which is going to be 0 over 4 minus 4, which is going to be 0 over 0, which is also undefined.
so that means it's neither continuous or discontinuous.
Now, man, we can we can we can work through it and get an answer. So we're going to look at what happens when we get situations like this. All right. So in a case where we have the 0 over 0, we can go ahead and simplify it. So this is, well, let me show you first so you can see, and then we have the discussion. So f of x is equal to x plus 2 over x squared minus 4. The denominator here is the difference of 2 squared. So we can write it as x plus 2 all divided by x plus 2, x minus 2. All right, that's the difference of 2 squares, because this can be written in the form x squared minus y squared, which is x squared minus 2 squared, which is going to give us x plus 2 and x minus 2. All right, so now that it is in this form, we see that the numerator can cancel here, right? So then we would get f of x is equal to 1 over x minus 2, right? So that's what we would have left. And now you
Change the
can
x to 1.
go again.
No, if you change the x to 1, sure.
No. The numerator, which is x plus 2, cancels with this x plus 2. So it leaves 1 in the numerator, because when it cancels, it leaves 1. And it cancel here, so it leaves 1. So 1 in the numerator and 1 times this that is left in the denominator gives you the x minus 2 same way. Following, or you're not sure, same way?
So me now I get it. Oh, I
All
get
right.
the one.
Well, pay attention. All right, look at this. Look at this. If we have 3 over, say 3/5 times 4/9, right? You would have learned that when you're multiplying, if you can reduce or cancel, you cancel. Take for instance, 3 can go into itself one time, 3 into 9 goes 3 times. So now you can say 1 times 4 to give you 4, and then you can say 5 times 3 to give you 15. You know that you can do that, right? Do you know you can do multiplication like this?
I'm gonna cross here one.
Well, this well, there's no when people talk about cross multiplication can only be done across an equal sign. So you have to have an equal sign in order to cross multiply. Either ways, if you have a fraction, like I say you have 2/6, do you know that you can reduce it by say 2 into itself goes one time and 2 into 6 goes 3 times, so you're left with 1/3. Do you know
Oh,
that you
yes,
can
sir.
do that? Then that is
Yes.
what we did right here. X plus 2 into itself goes one time. X plus 2 divided into this goes one time. So you still have the 1 here, so which is the numerator. See it right here, which is this one, because this x plus 2 cancels with this x plus 2. So just as though 2 canceling into itself one time, x plus 2 canceling into itself goes one time. X plus 2 canceling into itself goes one time. So they cancel each other. And then you have the 1 in the numerator and the x minus 2 in the denominator. Following the reasoning,
Yes, sir.
that is how we get it to be this right here. And now when you check it, you can go again now and check for x plus 2 and x minus 2. So when x is equal to 2, when x is equal to minus 2. All right, so when x is equal to 2, f of 2 is going to be 1 over 2 minus 2. So that's going to be 1 over 0, right? So this is going to still be undefined. So this is an infinite discontinuity. So when x is equal to 2, it is still undefined. So it is what we call an infinite discontinuity. All right? Because we know we can't divide by 0.
Yeah, when you finish, you can zoom out so you can take off this one, please.
Okay. This is going to be 1 over negative 2 minus 2, which is going to give you 1 over negative 4, which is just negative a quarter, right? So because you get a definite answer here, right? This is what we call now a removable. So this is now a removable discontinuity at x equal to negative 2.
Yes, so in with the topic of discontinuity and continuity, there are different types of them.
Yeah, man. Um, so when we look at the types of continuity, so this was the earlier part of the lesson. So the notes that was given to the types of continuity and the types of discontinuity. So this part is what we looked at first. What does it mean by a function is continuous, types of continuity, types of discontinuity, and how to prove that a function is continuous, right? So this is what
Yeah,
the
we
steps.
screenshot it.
All right, so start from there.
Yeah, zoom out, sir.
No, well, you would have to take two screenshots because if it's zoom out, it's going to be too fine. So you have this part now,
Hold on, sir. All right. Yes, sir.
and then this is would be the next part because at the bottom there, that's the last part.
All right. Thank you.
Okay, now we're back to our document. So please note so we can pay attention to something. When we use x equal to 2, it is undefined. When we use x equal to negative 2, it is also undefined because both of them are 0 as the denominator. All right. When we simplify the question by using the difference of two squares to simplify the function, and we get 1 over x minus 2, substituting x equal to 2 and x equal to negative 2. When x is equal to 2, the denominator is still 0. So that means we get an infinite discontinuity because the function is still undefined. But when we use x equal to negative 2, we get negative a quarter. Notice we move from where? We move from where it is undefined. When x equal to negative 2, we move from it being undefined to now it being defined. So because you change the function from being undefined to now being defined, the discontinuity is known as removable because you would have just removed the discontinuity part of it to now make it be um defined at x equal to negative 2. So that's why this one is known as a removable discontinuity. All right, because when it was once undefined, it is now defined. So it is known as a removable discontinuity. All right. All right, take that off, and then we look at a few more questions. You need more than that? Do you need more information than that to be displayed?
Yes, sir.
All right, let's start from there,
Yeah.
and then you
That,
can tell me when to scroll down. All right, let me know when you finish writing, please.
Yes, sir. I'm going, sir. Finish, sir.
All right, thank you. All right, let's. Say, for instance, you're given this one. Wait, did I give this one earlier? Oh, yes, I gave this one earlier. Sorry about that. Gave this one already. So I'm gonna use a different one. All right, so let's go ahead and check. Now this one, you see that the denominator is equal to 0. When x is -3 plus 3, that's 0. So we don't have to go through and substitute it in to figure that out. So we have to do some factorizing. So the numerator can factorize to give us x plus 1 and x plus 3, all divided by x plus 3. If you're not seeing that it can factorize like that, remember you have the quadratic. We look at using the AC method to factorize, right? You can use the AC method to factorize it, or just some people say AC method, some people say method of factorization. So either way, so these two will cancel with each other. So you're just going to have f of x is equal to x plus 1 when x is equal to -3. So you're going to have f of -3 is equal to -3 plus 1, which is equal to -2. So this is a removable discontinuity. at x is equal to negative 3. Remember, how do we know that it's removable? Because if we do direct substitution and put x as negative 3, we're going to get 0 in the denominator. That means it's going to be undefined, right? So the function is going to be undefined because you're dividing by 0. If it is undefined, then that means you have infinite discontinuity, right? Once you have 0 in the denominator, but the function is such that you can factorize and cancel. So that's why it is called a removable discontinuity. All right, because now you get a definite value for when x is equal to negative 3. All right, definite value. See value right here? Sure. Clear to see. Oh, this is at x equal to negative 2. Sorry about that. At x equal to negative 2. Now, when x equal to negative 2, we're going to have f of negative 2. That's when it's equal, so we have to use this one. So it's going to be negative 2 plus 4, which is equal 1, which is equal to 2. So it exists. So it's clear to see that it exists, right? You get a definite value, so we know that the function exists. Now, we can approach negative 2 from two sides. So here we have negative 2. You have a number to the left of it, negative 3. You have a number to the right of it, negative 1. So you can approach from the right side, or you can approach it from the left side. That's how you can approach negative 2. From the right or the left. If you're approaching from the left-hand side, so the limit as x is approaching negative 2 from the left-hand side of f of x. So it's going to be the limit as x approaches negative 2 from the left-hand side. Sure. If it is approaching from the left-hand side, that means the values of x are less than negative 2, which means we have to use this function. Because this is a function that as the domain values are the x values that are less than or equal to negative 2. So if you're less than negative 2, that means you're approaching from the left hand side. So you have to use this function right here, which is x plus 4. Because notice this function is for values of x that are less than or equal to negative 2. So this is going to be negative 2 plus 4, which is going to give you 2. And if you're taking the limit as x is approaching negative 2 from the right hand side of f of x, which function are you using? Well, there is only two of them. You have somewhere you can get 2, where you can get 3, 4 different functions. So because you're now approaching from the right hand side is where values of x are greater than negative 2. X is greater than negative 2, so that means you have to use this function, which is going to be negative 2 times negative 2 minus 11. So this is going to give you 4 minus 11, which is going to be negative 7. So notice these two are not the same. So since the limit as x approaches negative 2 from the left-hand side of f of x is not equal to the limit as x approaches negative 2 from the right-hand side of f of x, the function is not continuous, right? So what happens here? So you have what is called a jump discontinuity. At x equal to -2. Because when x is equal to -2, you're going to get two different values. You're going to get one at 2 and one at -7. So there is a jump between the points, or there's a jump between the function, which means that you have two separate functions. I'm going to represent this one. So you can see, I'm going to try to represent this one so you can see what this would look like on a graph paper. So I'm going to allow you to finish right and then show you what it looks like on a graph paper. Go ahead, please, and finish writing. If you have any questions, you can go ahead at this time as well. Um, Anybody can say what is happening? Well, I'll find out a little later.
What's wrong, sir?
No, man, a little later I'll check with you to find out what's happening.
All right, sir.
Let me know when you finish writing, okay?
So finish right now.
All right, so we're going to look at what this looks like on our graph. This goes all the way up to 7. And it's going to get more negative. I just need 2 points. All right. Sorry. Sorry. All right, so we're going to look at the two functions, x plus 4 . Remember, this is a straight line. And this is for when x is less than or equal to -2. So x is less than or equal to -2. So -2, -3, -4, -5. Let's see. -2, we get 2, -3, we get 1, -4, 0, -5, we get -1. So the points are -2, 2, -3, 1, -4, 0, -5, 1. Those are the points you're going to use to plot that line. So -2, 2. So we have a solid bubble. Right? And then, so we have a solid bubble to start because it says x is less than or equal to 2. So it's equal to it. So we use a solid bubble. And then -3, 1. That's a point right here. -4, 0. That's a point right here. -5 or -1. -5, -1. That's a point right there. So you would have a straight line like that, right? So this part of the graph is for x plus 4, right? And then now you have the next graph, which is x and f of x. This is now when x is greater than -2. But this is for the function f of x is equal to -2x minus 11. So -2, -1, 0, 1. We may not can use all of them, but let us see. -2, when x is -2, we're going to get -7. When x is -1, when x is -1, we're going to get -9. When x is 0, we're going to get -11. When x is 1, we're going to get -13. All right, can't use all of them. So at this point, -2, -7, -1, -9, 0, -11, 1, -13. Here, we're going to use an open bubble because of this reason. X has to be greater than -2, so X cannot be 2. You have to start there, but you have to know how to represent it. So when we start at -2, we're going to get -7. So right here, so open bubble at -2, -7. -1, -9, so -1, -9, that's a point. And 0, -11, that's a point. So -13, so 1, -13, that's a point. All right, so you'll have your graph, straight line going down like this, and this is where -2x minus 11 is. So this part of the graph is going to be the -2, -11. So notice there is a jump. All right, so this is what we mean by a jump in the graph. One line is all the way up here while the next line is all the way down here. So there's a jump in the graph. So it's not continuous. All right. So this is what the graph would look like when you talk about a jump. And we look at one where it's continuous up here already. So where one function stops, the other one picks right up. So it continues. All right, so let you write that off, and then we look at a few more questions. If you have any questions, you can go ahead at this time.
All right. So this is how, so in the exam I get to plot them, right? Yeah. Them are going to plot them in the exam.
No, normally it's given to you.
Oh, okay.
Yeah.
So when I get this, it already plotted. That tells you, sir.
Yeah,
Like
man.
draw a
Yeah.
graph and see. Oh, okay.
Yeah, man. So it will be already drawn.
And sir, the point the way I get, sir, oh, never mind, sir. Let's see where I get them.
Okay. Mm-hmm. Mm-hmm. Let me know when you finish writing, please. All right, so try these two questions for me, please. Let me see what you come up with for your answer. All right, try these two questions for me to prove if the function is continuous or discontinuous, and if it is discontinuous, what kind of discontinuity exists. All right, these two are very simple, so I'm not giving you a long time because we have just a few minutes before the end of class. So just giving you about 6 minutes. All right, so this was mistakenly written as a A, but it should be 0 as well. All right, not sure if you realize it, but it should have been 0. All right, let's go ahead um, and see what we're working with. When x is equal to 0, f of 0 is equal to negative of 0. So this is just negative 2. So we know that the function exists. Approaching 0 from the left-hand side or the right-hand side, the limit as x approaches 0 from the left-hand side. From the left-hand side, we're going to use this function. So we just get negative 2. And the limit as x approaches 0 from the right-hand side, we're going to get negative of 0 over 2 minus 1. So we're going to get negative 1. So notice they are different. Since the limit as x approaches 0 from the left-hand side of f of x is not equal to the limit as x approaches 0 from the right-hand side of f of x, the function is not continuous. It's not continuous at x equal to 0. So you have a jump, discontinuity. All right, so there's going to be a jump. And over here now, when x is equal to negative 3, f of negative 3, that's going to be negative 3 minus 4 over negative 3 squared minus, well, plus 3 times negative 3. That's going to be negative 7 over 9 minus 9, which is going to be negative 7 over 9, undefined. And then when x is equal to 0, f of 0 is equal to 0 minus 4 over 0 squared plus 3 times 0, which is equal to negative 4 over 0 plus 0, which is equal to negative 4 over 0. So it is also undefined. So this is an infinite discontinuity at x equals 0 and x equal -3. So there's no way to do a removable. So there's no removable discontinuity for this one. It is both denominators. So one of the indicators we can use is when you have a number in the numerator and the denominator is 0. When you have 0 over 0, you can get a removable discontinuity there. But when it's a number over 0, then it is just infinite discontinuity. So once it's a number over 0, you're going to have an infinite discontinuity. Hold just a brief moment.
So I'm gonna see a screen.
Yeah, I said to hold just a moment. Hold just a moment.
Oh,